So in your spectrophotometer measurements, cuvettes are very important, especially choosing the correct cuvette for your either UV or visible light wavelength measurement. Okay, that's important. And then maintaining the cuvettes are also important because quartz cuvettes are really expensive, glass one as well. But whenever you try to make the measurements using cuvette instead of a spectrophotometer, often you try to wipe off the surface of the clear sides of the cuvettes using maybe Kim wipes, things like that. And then when you do that, you tend to make a scratch on the surface. If you make a scratch, that's a damage, then they can hinder your observance readings. So try to make sure that you use lens paper, special lens paper for your measurements. Okay, and then once the cuvettes are done, they are recycled because we don't throw them away because they are expensive. You have to use the correct washing solution. So you dump out whatever the samples you had in the cuvette, and then you rinse them a lot with a lot of water and ethanol, and then you dry it and put it back to the original container. So take a look at your textbook to understand how you use the cuvette properly, okay, and the design of the spectrophotometer. So samples, of course, should come in a liquid form because that's how you're going to do the measurement. And then in that case, your sample should be well mixed homogeneously. If it's separated, if it gives you two different layers, your measurement is not going to be done correctly. And then you should not have a lot of bubbles. So those are not all good, okay? Because different solvents absorb different light different way. Okay, the light source, are you going to use visible light or UV light? Depends on your observance profile or what you are detecting. You have to choose the appropriate light. It's visible light is normally generated by the tungsten light bulb, and the UV light is normally generated by the deuterium light bulb. Deuterium light bulbs are fairly expensive, and they come with certain lifespan. So if you are done with the spectrophotometer, you make sure you turn it up. If you leave it on long time, you are burning the light bulb, which is the expensive part in your spectrophotometer. Okay, and detector in the cuvette, of course, so it senses the light that's transmitted through, and then it's going to convert it, okay, into electronic signal. So that's how the measurement is done. And the spectrophotometer comes in different function, different types. There's something called scanning spectrophotometer that has the capability of doing the measurement throughout the light range. So it can scan your sample ability of observing certain wavelength light. If you don't know where your sample is observing the light very well, especially if you have a mixture of samples, okay, then you can use the scanning spectrophotometer. Okay, and there's another thing called double beam spectrophotometer. What we have in our lab is a single beam because there's only one light source coming through, and your cuvette position will be changed. So that's how the measurement will be done. But there are old-fashioned spectrophotometer where you have double beam spectrophotometer. That means two lights will coming out from your light source. If that's the case, one light will measure your blank cuvette, and the other light you will use it to measure your sample. So the automatic calibration can be done simultaneously if you're having that double beam spectrophotometer. Okay. So spectrophotometry measurement can be used in qualitative application. What do you mean by qualitative? It's not quantitative. Like I said, if you want to know what's in your sample, if you know the identity of your sample or how many different things are present in your sample, okay, that's when you use this qualitative measurement, because it depends on what component you have, what molecule you have in your sample, their light absorption spectrum, the profile will be unique. Okay, for example, this diagram shows you what? Observance pattern of different metal ions. Okay, it's the blue one, nickel. Typically, you can observe the light well on about 400 nanometer. And then you can also observe the light around 650 and maybe 700. If you see a pattern like that, it's mostly made up with nickel ion. In contrast to that, if you have a sample that's made up with copper, for example, it doesn't absorb light around this area, but it absorbs the light well around 800 nanometer. So if you have something like that, that unique profile, that is most likely due to the copper present in your sample. Okay, so that's the qualitative application. Okay, so you can identify what things you have in your sample using a spectrophotometry, kind of scanning spectrophotometer. Okay, and the most often cases you're going to use your spectrophotometer reading in quantitative application. So like I said before, if you have a standard sample with different amount of your analytes, and then if you know their observance profile, so you can plot what standard curve. Once you have the standard curve plotted, you can get the mathematical equation for your standard curve. Okay, from your standard curve, if the observance equals whatever the amount of concentration of your analyte is. Okay, so if you can get that equation in the maybe in this form, in this simple form, okay, y equals slope times x. Okay, because y-intercept may be 0. It is 0 because what? When you have a blank cuvette where you don't have anything, that's the baseline of your observance. So in your spec reading, mostly you will have that equation. Okay, y equals slope times x. Okay. Then once you have that, it'll be handy because now when you have an unknown sample, okay, if you plug that unknown sample into the spec and read its the observance, that will be the a value here or y value, then you can get x value calculated. So that's how you can quantify amount of your sample using spectrophotometer. That will give you the standard curve and equation. Make sense? Okay, and then Beer's law is very important in the spectrophotometry analysis. In Beer's law, the observance value equals alpha beta. Alpha is the objectivity for that compound at the wavelengths, and beta is the path of the wavelengths, which is same as the size of a cuvette, and C is the concentration. So it explains the relationship between the observance you got from the spectrophotometer and the concentration of the analyte, okay, considering the unique objectivity of the compound that's found from your analyte and the size of the cuvette that the light has to go through. Okay, so that's the Beer's law. Observance equals objectivity of your compound times the size of the cuvette light path. Normally it's 1 centimeter, and times the concentration. If you change that equation to solve the concentration, same as observance divided by alpha and beta, and normally alpha and beta is known, and like I said, the beta value is number 1, and so mostly there's a correlation between observance and the concentration, kind of linear correlation. That's what Beer's law says. Okay. So assumptions in applying Beer's law in analyte quantification. The instrument is calibrated. It's in good working condition, of course. It should be well maintained. And the solvents, reagents, and assay conditions are consistent throughout your measurement. The blank when you measure it, and when you measure the sample, the conditions should be the same. And the relationship between the observance and concentration must be linear. Okay, what does that mean? If there are thresholds, you only take the relationship within that linear relationship. You don't take that relationship after the threshold. That's what it means. Okay, and then proper blank should be used to calibrate your observance. Okay, and the deviation from Beer's law at very high or very low observance level, spectrophotometer shows non-linear inaccurate readings. What does that mean? What it means is, after or before the threshold showing the linear relationship, let's say it changes, okay, like that, maybe S-shaped curve, then your linear relationship is only relevant within that, between that threshold site. Don't use that linear relationship to estimate the sample that is in very low concentration or higher concentration, because the linear relationship would not be applied to the very low concentration range or higher concentration range. That's what it means. Okay. And some components in the sample may interfere with your measurement, so you need to be careful. for example, the buffer that's dissolving your analyte, if that buffer has some special compound that hinders the observance, you cannot do the measurement. Okay. And quantification with spectrophotometer. Number one, color-based assay. We saw the colorimetric assay. Okay, example is your protein assay using BIOT solution. Okay, that is a good example. In that case, why do you have to add BIOT assay solution? Because protein themselves cannot absorb light very well, and because the proteins have different types of amino acids, light absorptions are different among 20 different amino acids. Okay, so there is no linear correlation between the concentration and the light absorption of the UV range. Instead, if you add a chromogenic substance like Comasi blue, brilliant blue, that blue dye will stick to your protein, and then once it does, then blue color will correlate with the amount of protein that you have. Okay, that's why you are using BIOT assay in protein quantification. Okay, so protein plus blue dye solution, the molecule, if we read that at 550 nanometer, which is the visible light range, or 595, there's going to be a linear relationship between the amount of your sample that's stuck with the blue dye and the absorption of those molecules. Okay, so that's why you use the BIOT assay. And then, so that's the quantification. And then turbidometry and analysis of cell suspension. What does that mean? So when you dissolve a bunch of cells, like cells floating in the growth medium, like E. coli cells or yeast cells, for example, okay, if you shine the light on those cells, what's going to happen? Okay, yeah, some light may be absorbed, but a lot of light will be scattered by those floating cells. So we can measure the turbidity of the cell using spectrophotometer, especially if we use 600 nanometer, again UV light range. If you shine the light on the cell suspension solution, actually the turbidity will come out. Okay, so the more cells are floating, of course, it's more turbid. So there will be less lights going through. Okay, so the amount of cells, okay, per your given amount of the cell culture, and the absorption, okay, which is calculated through the transmittance. Of course, transmittance will be correlated with negative log of 10 of the absorbance, right? And it's light scatterness is also reflected there. So you can estimate the number of cells based on that those relationships. Okay. So the absorbance of the solution of the cell suspension, although it does not represent real absorbance, has a linear relationship with the cell density of the suspension. So that's how you can use the absorbance of the cell suspension in cell concentration quantification. Okay, that's a turbidometry based on cell concentration analysis. Okay, and then kinetics assay, of course, when you do some kind of a assay on the enzymatic conversion reaction, okay, what you're going to measure is, of course, the conversion of substrate to the product, right? So hopefully that will be detected by your spectrophotometer. But you can also measure that within a given time to measure the speed of the reaction. Okay, so you can measure the speed of reaction conversion. Actually, so that's a kinetic assay. You can do the kinetic assay using the spectrophotometry. Okay.